Hello, I'm Andrea, and I will present our paper, Audio Retrieval from Natural Language Queries. Our aim and motivation is to be able to retrieve audio using free-form text queries. For example, let's look at this text query. A rolling train blows its horn multiple times. We would want to find the audio from our pool of samples that matches this text query. Now, here are 3 audio files that match this query. Okay, so some applications for text-based audio retrieval. One possible application is being able to search large audio databases using free-form language. Currently, most of the audio search frameworks require you to have an index database where each audio file needs to have an audio tag, which can be either a sound class or the title of a song. This then reduces to a text matching problem. Other frameworks allow you to use an audio query to find other audio files by sound similarity. However, this is not really an intuitive way of searching an audio database, since we as humans find it difficult to imitate non-human sounds. Another possible application is for creative applications. For example, we can search for a specific audio file that we want to insert in our podcast. And also, another possibility is using audio retrieval to enable cheaper, computationally efficient video retrieval by only using the audio modality. Now, for the remainder of this presentation, I will describe the audio captioning datasets that we have used. I will then describe the baseline model we employed. And lastly, I will talk about the retrieval results that we have obtained. So audio captioning datasets consist of an audio track and a text description of that audio sound. Audio captioning datasets are quite different from video captioning datasets because sometimes the image doesn't necessarily match the audio. One good example is taken from the AUDIOCAPS dataset. And for example, in this image, we can see that the video caption is a bus passing by with some people walking by in the afternoon. The audio caption is a muffled rumble with men and women talking in the background while a siren blares in the distance. So they are quite different. In our work, we have used 2 audio captioning datasets. The first one is called AUDIOCAPS, and it is a subset of the AudioSet dataset that contains videos. This means that AUDIOCAPS has, besides the audio component, some videos and the associated audio descriptions. CLOTHO is a much smaller dataset than AUDIOCAPS, and it only has audio tracks and the audio descriptions. Now, the baseline model we have used is called Collaborative Expert Model, and it was presented at BMVC 2019, and it was used for video retrieval, but we are using it for audio retrieval. So I will talk about this model for a bit, so you can understand how it works. There are 4 main components. The first one is a set of input expert features. Then there is a temporal aggregation component that aggregates these experts. There's a collaborative gating module that merges all of these temporal aggregated experts into one video representation. And lastly, there is a ranking loss for training our model. I will now describe each of these components in more detail. So first of all, we have the expert features, which are extracted from pre-trained expert networks. Since we are interested in audio retrieval mainly, we have used 2 pre-trained audio classification networks to extract our feature experts. One of them is VGG-ish, and it was pre-trained on YouTube 8 million, and one of them is VGG Sound, which is a ResNet 18. Then there is the temporal aggregation component. Since visual features are slowly changing, or more slowly than audio and text features, we are only averaging this. And then for audio and text features, which are faster changing, we use what is called a NetVLAD, which mimics the vector of locally aggregated descriptors, called VLAD, as a trainable network layer. So the idea behind VLAD is that you have multiple local feature vectors, and we want to cluster them in K clusters. Then we want to represent all of these features as the distance between the features and the closest cluster to them. For one audio file, we can have n audio feature vectors. Each one of them can have a dimension, say d, and we want to generate this matrix V that will have a dimension of k times d, where essentially each column k will represent the residual, which is the distance between xi, local feature vector, and the corresponding cluster to which it was assigned ck. Now, the next component is the collaborative gating mechanism, which aims at capturing complementary information from task-specific experts. It contains two steps. One of them is predicting attention vectors for all of the experts, and H and G are multi-layer perceptrons that model the pairwise relationship between psi I and psi j. Psi here represents the features that have been projected to a common dimensionality, and in the image on the right, you can see how these attention vectors are calculated for each expert. In this case, for expert 1, where we have 4 experts, this is the process here. Oh, sorry, probably show there. So this is expert 1, and then expert 2, and then we compare expert 1 with expert 3, and then expert 1 with expert 4. The second step is modulating the experts using the attention vectors. The reason we do all this is because we have multiple experts and we want to keep only the most important components of the feature vectors and reduce noise and redundancy. Lastly, the ranking loss is the contrastive ranking loss that we've used for our model, which is there to train the functions that generate the audio and text embeddings. And ideally, we want these audio and text embeddings to be in the same subspace. And whenever there is a paired audio and text description, we want the embeddings to be close. And whenever that's not the case, we want them to be far apart. Sij is calculated by cosine similarity between the embedding of the audio file and the text description. B is the batch size. M is a margin hyperparameter that can be tuned based on the application. And the square brackets represent the max between 0 and the value calculated there. Now I will show you some qualitative results obtained after training this collaborative expert model on audio features only on the AUDIOCAPS. So here we have the text query, water gurgling. Here are the top 3 retrieval audio files. Some images will show up when they will play. These images are not used in getting these results. They are just there for visualization purposes. So as you can see, visually all of these examples are quite different, but the sound is similar. This is the last example. So we have a police siren going off. In this case, neither of these 3 top retrieved audio files are the ones that actually come with this particular text query. However, the examples are quite relevant. So in the first one, we won't see a police car. But the sound is similar to what you would expect. Then we have a fire truck. And lastly, another example where there is no police car seen in the video. Okay, so now some quantitative results. What I'm going to present in the next slides in terms of histograms are all based on this metric called recall@1. Recall@1 means if you input a text query, then you will retrieve one audio file, and if that one audio file is the one corresponding to the text query, then that is counted as a correct result. If not, it counts as a wrong one. The same is true when we use audio as a query and then we want to retrieve the corresponding text. So here we have used some experts. I will explain them to you. INST corresponds to image classification, and we have extracted features from our videos using this pre-trained network. R2P1D has been trained for action recognition. We have also extracted experts for scene classification, but that didn't improve the results. And we have also tried transcribing speech and then extracting the features to see if that improves the results. But again, that was not the case. We believe it is because there was no overlap in general between what was being spoken and the audio description. So as we can see here, combining these two visual experts for image classification and action recognition gives a result of 10% recall@1. And then we look at our audio experts, since this is the task we are actually interested in. And we can see that VGG-ish by itself performs better than the combination of the visual experts. VGG sound is a bit better, and the combination of them two gives a result of 23% accuracy recall@1. Lastly, we have checked what is the combination between the best visual experts and the audio experts, and we can see a retrieval result of 28%. In this case, this is the reversed, so we have an audio query and we want to retrieve the best text. We can see again that combining the visual and audio experts gives the best result, but you might also notice that in this case, the accuracy is close to 35%. We believe that is the case because for AUDIOCAPS test set, we have 5 sentences for each video. So that means whenever we have video or audio. So that means whenever we have an audio, we have 5 options that are considered correct. However, when we do the text to audio retrieval, we have only one option that is correct. So this task might be slightly easier. We also tried to analyze the effect of the dataset size, since AUDIOCAPS only has 50,000 examples. And it's clear that the graphs are not yet saturated, which means having more data in the future can help get better results in terms of retrieval. Other data sources we have investigated are visual data sources. We have looked at ActivityNet, which is based on activities. As the description shows here, a close-up shot of a man riding around is shown. And QueryD, which is based on just visual description of the videos. Then the instructor places the strawberries in a container. Pre-training on this did not help, and also the text-audio retrieval on them was not that good because the descriptions are mainly visual, not based on audio content. Lastly, we have looked at the effect of pre-training on AUDIOCAPS and then fine-tuning on CLOTHO, and we can see that there is indeed an increase in percentage to almost 10% retrieval from 7. And we have also tried with a different retrieval model that is similar to collaborative experts, but it doesn't have the collaborative gating I've explained earlier. We can see here there is also an improvement, but the results are overall slightly worse. So in conclusion, we have introduced new benchmarks for text-based audio retrieval on AUDIOCAPS and CLOTHO. We had adapted existing video retrieval methods to the audio retrieval task, and we have concluded that frameworks would benefit from having more training data. Thank you for listening. More examples and also the code can be found on our project page.
Yes, so questions? Yes, please use the microphone, which is up here. Over there in the corner, way over there.
Yeah, on the chair.
Okay. Thank you very much for a very nice presentation. I wanted to ask for the audio analysis neural nets, like this BGG and ResNet style. What were the targets? Were there some sound classes or some sound scene, or how were they trained?
Yes. So we had the labels. The people who trained the networks had the labels for the sound classes.
Okay.
Other questions? One point I could make is that so many of these databases seem to be based on YouTube videos, but there's so much variability on YouTube. Is there any attempt to control, standardize, or is it just you just use the heterogeneous data and just go with that?
I guess it's difficult to get annotated data, and that's why YouTube is an easy go-to option. But definitely having a more control on the data set used can help us understand better what exactly works and what doesn't.
I was struck by one of your early examples that you showed an image with players on a field, and it's this text description says a specific name of a person playing with other players. But I mean, without context, how can you possibly relate which one of the people is the player in question?
Yes, that is a fair comment. Unfortunately, that is a problem, at least for audio datasets. The resources are so scarce, it's quite difficult to even think about all of these details. We just use what we have.
Right. And then there's the issue of what's the focus. You're talking about the scene is described as a bus with people passing by, and then you have different non-stationary sounds, and what is the main focus there? Or is it the idea to be there are several sound sources there, and the text description gives you a hint about that?
Yes, so there's no there is not a lot of guidance on how to describe sounds. But ideally, yes, we would want to have as much description as possible, and then maybe even work on trying to localize which sound where it is. But
has anybody or you ever tried to count the number of possible quantifiable sounds? How many are there?
Well, no, I haven't. But
we're talking millions or thousands, or
I guess in current experiments, maybe hundreds. And in terms of sources in one particular audio file, I've encountered up to 3 or 4 by looking at examples. So, maybe you have someone speaking, and then you have a ship making sound, and then there's like a train going on.
How big is the vocabulary used in the captions? That I could give an indication of.
I don't remember from the top of my head.
With order of magnitude, I mean.
Thousands of words.
Yeah, that's not that much.
No. And generally the descriptions are quite short as well, so they're not really far away from just saying this is a train. It's maybe there is a train in the background, so there's not a lot of variation in there. It's just like closer to a sentence, but not really descriptive.
Is it easy to find an out-of-domain example?
Sorry, what do you mean about that?
Out of the, something that did not occur in your training set, but to come up with a new query.
Oh, I see what you mean. So far, I don't think we tried to search for something that was completely out of the domain of searchable sounds. I guess that's just how far our brains can think in terms of describing audio sounds, and that's why.
Is it very accurate? For instance, in the example that you gave, the train having multiple horn. Yeah. So if you just ask for a train horn, is that?
Oh, I don't think there would be a big difference in
the response that you would get?
I think the response would be quite similar, because probably the sentences are not descriptive enough to actually, and we don't have enough data to discriminate between these small differences.
Then I have a very practical question in your paper. There's figure 1, which gives examples of correctly retrieved audio and failure cases.
Yes.
And The two seem to be the same.
Oh, do they? They should be different.
Is that an error?
Oh yes, that is strange.
Okay.
Sorry about that. Yeah, I will have a look and update it.
Yeah.
Yeah. Thank you. I didn't notice that.
And you have one question.
Ah.
Oh,
Have you tried to find human vocal sounds, laughing, crying, sad scene, or happy scene, etc.?
I think, yeah, we've tried laughing, but we didn't try emotions or anything along those lines. We tried human speech, we've tried laugh, but I think that was about it in our example search.
All right. Then I think.
okay. We'll move on. Thank you.
Thank you very much.